Hello everyone, and today we're back again on AtCoder Beginner Contest 323. As usual, we're going to use the CPA Judge extension and the competitive companion extension for Google Chrome to parse our problems. Also check out the other videos on my channel as well. Don't forget to subscribe, like if that helps. You. Yeah, as always, we're just practicing here on AtCoder. We try to solve as many tasks as possible, of course. And yeah, that's pretty much it. There's also videos on my channel that explain other concepts as well. And usually at the end of the competition, I try to go over all the problems and explain them each individually quickly, as well as I'm doing a live commentary across the whole competition. This will be available on YouTube after the contest. So when the contest finishes, this will be available. This is due to the so we don't want any, of course, cheating. That's the rules. So yeah, we have interesting score distribution here. This is the first time I see some interesting score distribution. The first three problems should be fairly similar, then a lot more harder problems, D, E, and F, and G. With this kind of score, I believe it's a really difficult problem. But okay, we'll see. Okay, we open the first three problems. You're given a string S consisting of 16 of length n 16 if the ith character of is 0 for every even number I, print yes, otherwise no. So we just want to quickly check if that's the case. So let's say that this is the case. Then for every even number from 2 to 16, from 2 to 16, if I, here we can just add +2, if it's 0, so I want this to be 0, then if it's okay, that's yes. There are n players, number from 1 to n, who have played a round-robin tournament. For every match in this tournament, one player won and the other lost. The results of the matches given n strings, each following the format. If this is not equal, then it's either won or lost. The player with more wins ranks higher. If two players have the same amount small ranks, report the player numbers in descending order of rank. So this is just a fairly simple problem. We'll read the n strings, then we can have a vector where we have the ranks for the n strings. There's count, how many wins he makes. If s of ij is equal to, what is a win now? O is a win. So ranks at I is equal, we want the most wins, of course, and the least rank. Then we want to sort ranks and by in reverse order. I think this should work. The programming contest World Tour Finals is underway, where n players are participating and half of the competition time has passed. There are m problems in the contest, so the score AI of problem I is a multiple of 100 between this and that. For each of the n players, you're given a string SI that indicates which of the problems have been solved. SI is a string. Okay, the total score is calculated as the sum of the scores plus a bonus score of I points. For each answer the question, at least how many of the problems that player I has not solved yet must player I solve to exceed all the other players. Note that under the conditions in the statement is always defined. Here the players plus a bonus score of I points. This is his bonus score of I points, of course. Okay, B gets accepted, A gets accepted. So this is straightforward, again, just implementational problem. And. So what was N? M was players and M was problems in the contest. Each problem had some score, so let's just say so these are that. Then for each player, so I need to rank to get the score for each player. Score, current score. Of course, m problems. If A of J is this, then current score of the player will be score of the J problem, and then the current score of the ith player would also equal this, right? Bonus score of I points. Then, okay, so we have some scores. Then what we want is to answer what is the minimum score is what is my maximum score. So max score so for each player is how much I miss. So what is the score I need to miss? Miss by how much? Miss is going to be equal to max score maximum of 0 and max score minus current score time. This is by how much I miss. And then the idea is that I need to sort the problems and I need to go through each player's problems and the problems that he hasn't solved, sort them in ascending order. What is calculate what is the minimum amount of problems, right? Many problems that have not solved by players. How many of the problems the player has not solved must player solve to exceed? If this problem is not solved, then I can use it. And then I want to sort the problems in descending order. If problems at if current score or no, if miss of I is smaller or equal than 0, break miss of I problems on J count plus. Okay, this should work. Now the more harder problems. Initially there are so let me just see. Okay, this gets accepted. Initially there are n sizes of slime specifically for each of the sizes. There are CI slime, so the count of slimes with that size. You can repeat slime sentences any number of times in any order. Slime sentences performed as follows. Choose 2 slimes of the same size. Let the size be x, and the new size 2x appear. Okay, the guy wants to minimize the number of slimes. What is the minimum number of slimes he can end up with? Optimal sequence of synthesis. I will push all of the slimes to two of these minimum number of slimes. So I push all of the slimes to 2, and I push all of the slimes to 2, and then I think so. What is this? First the size of the slime, and then the count of the slime. Can I do like a map here maybe? Then get an iterator. Will that work? So iterator dot first, iterator dot second divided by 2 is new size. No, new count. New size is iterator dot first times 2. Iterator dot second minus so this iterator dot second minus new count times 2 map at new count plus equal new size. No, map at new size plus equal new count. Okay, this works. There are n songs, each lasts ti seconds, has started a random play of the playlist at time 0. Random play repeats the following. Choose one of the songs from n with equal probability and play till the end. Here songs are played continuously. Once songs end, the next is chosen and starts immediately. The same song can be chosen consecutively. Find the probability that song 1 is being played x plus 0.5 seconds after time 0. Find what is the probability that song 1 is being played after this amount of seconds. Okay, D gets accepted. Module this. Okay, so probability, the songs are 10 to the 3, which means that it's only 1000 songs. And there's not many seconds for one song as well. 10 to the 7. 10 to the 4 is x. So you only need 10 to the 4. What is the probability, right? So what is the probability the first song is played? And then there's this probability here, and then for each of the songs it was not played. So yeah, I think I kind of know how to solve this. So there's n and x. Yes, 10 to the, yes. So let's just do max equals this. So I can do that. And then I need what is the time length of each song. So time, there's n songs, I need to read them. Then I'm going to go from time 0 up to some maximum time. This is what time I'm starting a song at. And then what song am I starting at? from here, from this time. So I have some probability. How do I do this? Wait, so the probability has to be expressed with modular arithmetic, right? Is this the same module? It's the same module. So, okay, so let me think about this. The probability that the first song that this song is played is, so essentially the probability that on DP0 this song is played is 1 over the, so essentially the probability from this song is being played from 0. No, the question is, what is the probability that this song is not being played? The probability that this song is played, of course, is 1 over the amount of songs, and n minus 1 over the amount of songs is that this song is not being played. So to come to some point here, that where some song is being played first, then this is that n minus 1 over n is the probability that I come to here. I need to wait this long. Then there's some probability that this song is played, so there's some probability that this song is played here. But then there's some probability that this song is not being played. So what if we have like this? What is the probability that, just see the standings. Okay, the probability that, okay, first like this, the probability that at zero, what zero means that this song is not being played, is n minus 1 over n. dp of 0 and 1, if this song is being played, then this is 1 over n. There's this probability. Okay, probability that, so the probability that has to set up some range here to range add. So the idea is from 0 to the first song where this first song ends. The first song ends in the second time of the first song, right? So in all this range, I want to set up this probability. Okay, this can be done with accumulative sums. Then the next idea is, okay, we have some probability that we're not gonna play this song. So what's the probability here that we're not gonna play this song? can we just push it somehow? If I come to here, all of this would have so dpi 0 means what's the probability to there on the ith index. We haven't still played this song. We haven't still played it. And what is the probability of I1 that we have already played? We have already played. And thus, I just need to make an accumulative. So what is the probability that we have already played this song? If I haven't, so from point 0 I add to point time of time of the song. I add this probability that I end up here. I add some probability that I end up here. Some probability that I end up here. I add these probabilities. Then I ask what is the probability. Okay, what is the probability I end up here? So there's some probability that I play the song. There's some probability that I skip it. Yeah, so okay, so there's no need of this essentially. I will calculate the answer according to a thingy here. So I will do this for each other song. So I will do this. The answer is of course 0 at first, right? So what is the probability? So dp of 0 is 1. Ending here is probability. So the probability of dp of t times the probability I end up having this song is this. So of course I can just do that. The answer will be that. And then if so my new time is my time plus the time of the song. If new time is well above, so I want only to like x to go to x. If it's well above x, then I want to continue. If not dp of new time, I will add what is my probability at t over this song, right? And then essentially I want what is my essentially I just want the answer here, right? Maybe okay, so probability at that song, the new time is my time and that song's time. New time. So because I end up having this probability, I just essentially want. Wait, no, I want to play the song exactly there. Find the probability is being played exactly there, so it's not like previous. How much it is exactly there being played. So exactly there is what is the answer is. I'm going to say that the answer is if the time is in the range. So if my time is in the range of x minus the time of the first song, and the time is in the range that, so the time is smaller than x plus time of the first song, then I want to add the probability. Right? I don't understand this. X minus time of the first song and x plus the time of the first song. Why does it crash though? X is 0 here. What is my probability that is 0? It's my probability Wait, what? I want to go to X because, or no, I want to go maybe a bit further. I don't know if I want to go a bit further though. If time is between, if I want the text to be played this song, it's either this or up to X, no? Okay, let me just print out all the DPs here. Not that I could actually see something from this due to modularity, but so there's 1 and 0 and 0. But yeah, no, not on up to n, but to max. It's asking what is the chance of missing exit play this at this point. Or actually, click is just like -1 errors, right? Now the idea is that, okay, so this is some probability that I go here, and there's some probability that I go here. Then there's some, the song 1 will be playing 1.6.5 seconds after time 0 in song 1 1 1, song 2 then 1, song 3 then 1. So that's one probability, that's one probability. Also there's one probability where song 1 is being played. So this is one probability that song 1 is being played. Okay, this looks correct. Okay, this looks correct. Just clear this out. Up to X. Up to X. I think that should be correct. Okay, so task F. Takahashi and the cargo are on a coordinate plane. Takahashi currently on some coordinates and the cargo is on some other coordinates. He wants to move the cargo on some third set of coordinates. When he's at X, Y, he can make, if he can move here, if the cargo is at this position, the cargo moves one step. So yes, so he can shift essentially the cargo around. Okay, find the minimum number of actions to move the cargo, and the points are really big. So okay, he gets accepted. That's good news for us. It's really good news for us because we will have now time for F and G. Have 1 hour for both. We're given some permutation for each k. Find the number modulo this of trees with n vertices. Number from 1 to n that follows among the pairs of vertices that are smaller directly connected by the edges. Exactly k pair satisfy this condition. This is an incredibly complex problem. So okay, so we have to solve F. The idea is that so he can push the cargo around. So if the cargo is here, then he can just budge around and then budge it around. So there's a strategy always. Probably just the idea is just to compute if the cargo is this point and we want to get the cargo here, and let's say that, so the idea is now where is Takahashi or whoever that is, Takahashi, where it is. So if the Takahashi is here, he can move to the cargo here because because man had distance, then he can push the cargo up to this point. Then he can move 2 steps and push the cargo there. So 2 steps are always required. So if the cargo and this guy has the same y coordinate, then Takahashi only needs to somehow come to the cargo and do this. It is not optimal to do anything else because you can push here, the car goes here, then we need to push again from there. So I think it is only optimal to do this. So now the problem is, okay, if Takahashi is here, then Takahashi needs to go like this. So there's like here and here, there's, what about here and here and 2? So however that Takahashi actually does it, it's still the same idea. So Takahashi needs to correctly position himself to the cargo, move the cargo. Now it's just if cases, right? As far as I can see. If the cargo and this position is on the same side, okay, so let's do if cases. Implementational task. So there's first is what? Takahashi tx ty, then the cargo x, cargo y, then target is going to be goal x, goal y, something like this. Okay, now the idea is to know where Takahashi should position himself. First idea, yes. So first idea is to get. Step one is get the position of the where should Takahashi position himself before moving the cargo. And the second thing is calculate the steps required. Notice that here there's an edge case where the position where Takahashi has the same coordinate is the position where same coordinate but like are in the middle of them. So there's a lot of cases here that we need to cover. So if the Takahashi's positioning is after the cargo box and the Takahashi position. The cargo box it sits in between those, where Takahashi position is equal to position, or there's the other edge case where this is y here. This is an edge case. But then after calculating the steps, we will assume that Takahashi can come to there, right, with the Manhattan distance. And now, being there, now we have to calculate the steps required to move the cargo. And now to move the cargo, there's a case where cargo x equals goal x, and there's a case where cargo y equals goal y. And there may, so the cargo is not equal, nor this is equal. But Takahashi can't be on the goal itself. Kind of matter. So that's the idea. Okay, there are these positions, and then there's like else. Else is quite an easy one, I would assume. So I think these are the steps. So in order to calculate first px and py, where that position has to occur, we need to see how the cargo is cemented onto the goal, right? So px, the position x is essentially if cx is smaller. So what do you know about there? So if cx is smaller than the goal x, so there are, okay, px is cx, py is cy. If cx is smaller than goal x, then px is cx minus 1. Else, if cx is bigger than gx, px is cx plus 1. And this is the same idea with y coordinates. So there should be x, there should be p, y, p. Okay. So now we have this first step, calculate. The second step is, so we have to be there. We have to come to there, right? So how to come to there is the how can we position there? So if px is smaller, come on, like how can we? So the edge case is this. If it's smaller than cx, what if it's equal to cx? So this is only if it's smaller, I would assume. So if px is smaller than cx and cx is smaller than tx, while ty is equal to py, so they're in the same y plane, but the x is smaller than this guy, then this is this. So I need to make the answer is, okay, so let's make a function here. Manhattan distance between x, y, dx, dy. So I want this distance plus, no, this distance plus this distance, right? On the absolute value. Right? Yes. So the answer should be Manhattan distance from px from txty to pxpy, plus there's one there, then there's one there, plus 2. Now the same idea is, what if I have py instead of this? Then the answer is the Manhattan distance between txty and pxpy plus 2 again, because I need to go there and to go there. The Manhattan distance. So that's that. If it's other thing, then that's just the Manhattan distance. So now we're at this position, right? Now we're exactly at the position we want the cargo to flip. Now we need to calculate the steps required to move the cargo. There's this thing here. So if the cargo position equals to the goal position on the x coordinates, then if that's the case, then we need only to move the cargo to the goal position. Plus 1, I think. Is that correct? Yes, that's correct. Because I'm moving 1, 2, 3. Or no, not plus 1. No, I don't need plus 1. That's that. Or if the cargo positions are equal to this, is essentially the same. But there's a problem if this is not equal. And essentially it means that the cargo needs to be moved like that. So it's still this, but there's an additional thing where we have to switch one, we have to move, so we move it like this and like 1 and then 2. So I think plus 2 here. But there's 3 here, which means that, oh, maybe it's good. Of course, this has to be 1 console. So we're off. We're a bit off. Let me take a look at the example here. So we say 3 and 2. What is our position that we need to do with that we need to move? Four and 2. Is that correct? Is that correct? Okay, so there's the 1 and 2. Okay, so let me draw a grid. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 7, X and Y. So we're at position 1 and 2. We're here. The cargo is position 3 and 3. Just here is the cargo. And the goal is position 0, 5. So this is the goal. So I need to move to this position. Oh, maybe because the goal is here, I only need to move to this position to get the cargo back there. I don't need to move to this position. So there are two possible positions I can move the car. One position is like this, another position is like this. What if the goal is here? Then if the goal is here, then I cannot move to this position. I can move only to this position. So, so there are two possible things that I need to count. Can you say that? Can you compress this to like a really small search space and say, well, search. Is it possible to compress this? I mean, it is possible, but I don't know if I want to. So there are two positions essentially. One position is, okay, so okay, there's this. If Cx is equal to, okay, so let's go over all of them. So if C equals to Gx, what does that mean? That means that there's only one position. That means that we kind of want only one position. That's the, so if x is equal, we want y to be smaller or big, want to be. Now depends on whether or not if cy is bigger than gy, it means that we want to solve for c if it's bigger, then we want to go cx cy minus cy plus 1, right? Else we want to solve for cx cy minus 1. Else if cy is equal to this, then depends on x, we want either to solve it like this or to solve it like this. Okay, that's one possibility. This will be done internally here. So, but what if they're not equal? So, if they're not equal, it means, okay, so first of all, if cx is smaller than gx and cy is smaller than c and then gy, then it means that this is here and this is here. We can move either to here or we can move to here. So we can solve for the position, the goal, yeah, the goal is here. So for the yeah, so this case is where the goal is here and this is this and then this is that. So we want to move either to this point or to this point. If the goal is smaller, we want to make it plus on this side or plus on this side. Else if cx is bigger than cy and no, then gx and cy is bigger than gy. This is the same idea, but now we want negative signs here. Now it gets a little bit complicated if one of them is bigger and the other is smaller. So if cx is bigger, it means that wait. Cx is smaller than, if cx is smaller than gx, it means that we need to go to this side. If this is minus and this is plus. Now the idea is, what if What if it's like that, right? So cx is bigger in the x coordinate, but it's smaller in the y coordinate. So we need this and this. So we need one is solve for the coordinate where this is smaller. Solve for cx and cy minus 1, or solve for cx plus 1 and cy. Cx cy minus 1, solve for cx plus 1 cy. And at the end, it's probably the same idea, but what if you have the gx coordinate here, and in cx coordinate here? Cx is smaller, but gx is cx is smaller and the gy is big. This case is cx is smaller. So in this case, we want this point and this point. This is cx and cy minus 1, cy plus 1, and cx minus 1, cy. Cx minus, so cx plus 1 minus. So okay, so we have this already done. So we know what position we need to be stationary at. Know what position we need to be stationary at. But now the idea is that, okay, so we know what positions we need to check. Now idea is that, okay, so if the target is equal to this and then that. So what is this? How is this related? 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. There's 0, 0 on Takahashi. The goal is 1, 0 is the cargo, and minus 1, 0 is the minus 1, 0 is the goal here. Takahashi needs to move 1, 2, 3, 4, 5, 6. So Takahashi has to move to here. So the position here, I believe, has to be 0, 2, 2, 0. So this is the position Takahashi has to move. For Takahashi to move there, it's like 1, 2, right? But then there's 2 here, 1, 2. And Takahashi moves there by this position. And then the answer here has to equal to Takahashi here, it's equal to this. If py is smaller than be, or it can be the other way around as well, right? What if we have the idea that it's like this, no? Now, also, we need to come up with here the same thing. Okay, so that's 4. And then we need to move this. So let's pick a case where, okay, so let's say that the goal, let's say that Takahashi is here, right? The goal, this has to be, what if the cargo, the goal is here, the cargo is here. What if you have something like this? Takahashi is at 0, 0, goal is at 2, 0, cargo is at 3, 0. No, cargo is at 3, 0, goes to 2, 0. There's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. That's 7. What if there's the goal at, what if the goal is somehow here? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The goal has to be at position 0, then here 5, 6, 7. So here that should be 7, right? Four, 0. That should be, that's 6, 1, 5, 6, yes, that's 6. And then there should be a Manhattan. The Manhattan distance is 1, 2, that's correct, that's 10, but that's not correct. That's 8. If I'm standing here, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. It's correct. 1, 2, 3, 4, 5, 6, 7, 8. Well, that is correct. So, oh, wait. So you're saying that that is correct. I mean, to be honest, I don't believe myself. That is correct. Okay, so we solved this. And now we kind of want to solve G. But there's no time to solve G, really. You're given permutation P and find the number modulo this of trees with n vertices and satisfy among the pairs of vertices U and V. U and V that is smaller, that are directly connected by an edge in the tree. Exactly K pair satisfy the permutations. Come on, this is quite possible. They're direct. The number of trees is very closely connected to the Kaplan numbers. PU and PV. Exactly K pairs means that for UI smaller than VI, there's inversions. So we want K inversions of this between these two vertices, right? So what if we say that, okay, we have each pair, right? I mean, we can count the number. So okay, let's connect them in pairs, right? Let's connect them to their inversions. So each inversion, they're at most n square inversions, right? So n square inversions among the pairs of vertices UV that are connected, exactly K pairs satisfy. So exactly K edges in the tree are inversions. So n square inversions, there's n square inversions, and we need to order them for each K. Yes, so okay, so for each inversion, okay, we will build a graph. We will build a graph from the permutation, right? So let's say the graph is something like this. Doesn't matter. It doesn't quite matter how it looks, but let's say it's something like this. Then we want to take K of these, and for them to form a connected. So sometimes it could be zero, right? Because there could not be a connection, but okay. Yes, so there are key connections. You need to see if I take this inversion and I don't take this. So this is okay. This has to be first a graph, right? But then you want to how many so we want to take some k edges. For each k we want to take some k edges, and then to be a tree. So this cannot be a graph. So minimum span, so not a minimum spanning tree, but a spanning tree in the graph. Okay. Can this be a spanning tree? Like all of the pairs of the permutation. Like all of the what if I take one edge small? So I'm given a graph and I want to take k edges. Is there some permutation property that here always satisfies? Is there the case that, okay, so let's assume that this guy is bigger than this guy, so pi, pj, and pk. Let's assume that pi is bigger than pj. Let's assume that pj is bigger than pk. It means that pi is bigger than pk as well. So when there's this inversion and this inversion, there's also this inversion. So it's a transitive thing. Okay. Then if I, j, and k. But then, okay, so imagine, okay, so this is transitive. Now, due to the transitivity, can we divide them in like components or something? So what if this here is bigger than this, but is smaller than I? So it can be like this. So there could be some here. So okay, so like that's PU. Let's see. How many trees? How many do I have to take if I have k edges to this to be a tree? This node and this node has to have one edge. Or no. I mean the number, and I want to calculate the number of spanning trees. The number of spanning trees in a graph. This is what I want. If a graph is complete, now finding the number of spanning trees in a given graph. Counting spanning trees. Number of spanning trees in a graph with k edges. That's all. Calculate the number of spanning trees. The number of spanning trees is equal to the number of spanning trees in graph minus where e is the edges of is equal and where e is any edge. E is the deletion of the edge and this is the contraction of the edge. This gives you a recursive way to compute the number of spanning trees in the graph. The cut vertex, a vertex which removes separated number of spanning trees can be found multiplied together. Yes, but that we don't have cut vertices and all we won't have found. There are many examples of rules as complete bipartite. This is definitely not a bipartite graph. The matrix 3 theorem gives you a formula of the number of spanning trees. Of course, you must know more than just the number of spanning trees after all. Matrix 3. There's also Kirchhoff's theorem. You take the Laplacian matrix of the graph, delete an arbitrary row and its corresponding, and find the determinant of the matrix, the value of the determinant of the number of spanning trees for the graph. Finding the determinant of the matrix is a hard problem in itself. Like takes cubic time or something. So this is not good. This is not good. Matrix 3 theorem, also called Kirchhoff's theorem. Yeah, but that's. By the way, this guy also is just like we're deleting is equal to this plus. So when you delete this edge of the graph and plus when you contract the edge, but that's not if I contract the edge and you gain n minus 1. So let's no, this is way too complex. No, this is way too complex to calculate. So given this matrix theorem or Kirchhoff's matrix theorem, then this is fine, but this calculates us very slowly. Counting spanning trees. There's some maximizing the number of spanning trees. Spanning trees with k edges, this is very important as well. Like spanning trees, not only that they have this so you need to calculate with k edges this graph. One vertex, if I want that vertex to be inside the graph and it has like only degree 1, then that degree has to be taken. Otherwise, there's a choice whether or not you take one of the degrees or the other degrees, right? So, or the other edge. But then you come across, to satisfy this, you have to take either this and this. Then, okay, so you push like a BFS or something, but then it's not easy. So there's something with this transitive thing of the inversions here. This allows us to do something that otherwise the problem won't be solvable. I don't know. I won't solve this one. So I will need to think a lot about this one and to come up with some idea. But okay, so let's go over the problems one more time. But I think I explained all of them really well. The first problem A, I won't even try a lot to explain. We just started the auth index here, and then we skip so for each, not auth, even I, but I here because it's zero index. It's auth actually. So we go like this, and we try that. We check if everything is zero, set these indices, then it's okay. This means that we're going to end okay with all of this. So that's pretty straightforward, and then if it's okay, it's yes, or otherwise no. For B, we're given some kind of a matrix, and we know that what each player has won and lost against the other players, because it's a round-robin tournament. Each player plays with each other, except himself, of course. So we will create an array with ranks, and what we want is to count what are the current rankings of the players. So we will create the array, and then we will iterate, and we'll count the wins. This is the wins of the ith player. We will sort first by wins and then by the index, but the index will be negative here, and thus, because we want to sort at the decreasing order of wins, so we want the biggest wins first. But if they have two the same wins, then what we want is the smallest index. So biggest wins, smallest index. That's why it's negative here, just not to. I didn't want to make a custom operator and do this, but just negative here. And we sort them in reverse order. Then to print out the indices, we need to negate this negative that we have here, and then +1 to just put them in how do you say it, in a one indexed, so to print them. So instead of 0 being here, 1 being 0, we want to print 1, right? So this is 1 and 0 indexing only. So C is a bit more implementational. You have again this kind of an idea, which so you have some problems. Each problem has some score, and then every player has solved some problems, but no player has solved all of them. This is due to the allowing. So this is just to make the problem always defined. So you have each problem has some score, and then some players solved some of the problems. So this player solved this 2000 problem, this player solved these two, and now your question is how many of the unsolved problems for each player the player has to minimal number of unsolved problems the player has to solve in order to be first place. If the other players don't solve anything in the meanwhile, right? So first we take the scores, we take with each player what problems has solved, we calculate the current score of each player. So the current score is just the sum of all scores, and then we add this here, I+1. This is due to the fact that they say bonus score of 5 points. Each player has a bonus score of 5 points. This is due to the definition of the problem. You can prove that mathematically it will always exist if you have this bonus score. So the bonus score is added here, but then you want to find also the maximum score. The maximum score is essentially telling you how much you need to win. Essentially used to tell you how much this player has to score in order to win the tournament, so to be the first ranked. So this miss is how much he actually needs to score, and this is the difference between the score and its current score, the maximum score and its current score. So okay, so we know how much he needs to win. Now we need to see what is the minimum number of problems he needs to solve. So this is, we will put each unsolved problem in some problems array, the score of this problem. We will sort them in decreasing order, and we will keep the count how many problems he needs to solve in order this miss to go down to 0. If it's already down to 0, then we just break. But if not, we will solve the most difficult problem and we will add the count. And if still it's not enough, then we will go solve the next the next less difficult problem, and the less difficult. But we will always be able to win if we solve all of the problems. And that's why that's why here it says that no player, here none of the players have solved all of the problems yet. This is a very important thing. Otherwise, it could never be possible. It could be a case where this could never go down to 0, this miss. So this is problem C. Problem D. Problem D is pretty straightforward as well. We have some slimes where each slime has some size, and there's some count of them of this size. And we just make a map for each of the size, how many slimes do we have, right? And we will iterate from the beginning to the end and say the following idea. We will say that the new count, so we will try to convert, so this is in sorted order, we are iterating in sorted order, and we will try to convert the current count of slimes as much as possible. We'll take these as much as possible and we will divide by 2, because now there will be half of them. Essentially, for each 2 slimes, there will be only 1. And this is the new count of slimes. The new size is twice as big, of course. And then this here, the current count will be minus this, minus the new count times 2. So this is just taking all of them and breathing them out, essentially deleting them from the current count. And then in the new size, we want to add the new count. And because this is all divisible by 2 here, we're always dividing by 2. So if we have 40, we will then have 20, then 10, then 5, and so forth. So we're dividing it by 2 all the time. This will be only logarithmic time, needed in logarithmic time. So essentially, this is n log n thing here. And then the count is essentially how many slimes in this map have a count, how many sizes of these slimes have a count bigger than 0. And this, we can prove that this is optimal, that this is the minimum number of slimes we can end up with, because no other slime can, if it's alone in itself with that size count, it cannot breed, it cannot make this synthesis or whatever, because you need to choose 2 slimes in order to make this synthesis, right? But that's pretty much it. That's a pretty good fast problem also. Problem E, interesting problem in itself again. So problem E, as I explained, we have some n songs, and we want to essentially say what is the probability that song 1 is being played x plus 0.5 seconds after time 0. Okay, so the idea is now here to use DP, and the DP is essentially for each of the time up till x, we want to say what is the probability that we get there, we start there a new song, right? What is the probability at that time it starts at a new song? But if time is somewhere where if I start a song there at song 1 and it takes time 0 to play, x will be as well in the mix, right? X will be a point where essentially if I have x being here, if I start song 1 here somewhere and it takes this long, then at this point x, we will be still playing this song 1. So this is song 1 being played up to here. So we want to, if x is here and we know the length of song 1, we can start song 1 anywhere in this. So from here to here, anywhere that I start from here to play song 1, it will still play here on the x coordinate, right? It will still play. But if I started after x coordinate, this doesn't matter because here we already missed it. If I start somewhere here, song 1, this doesn't all matter because it won't play on the x coordinate. It's not far enough. So we just want this here. We just want the sum of all of these dp's divided by n, because there's only one chance out of these n chances that I start here a song. That is song 1. Otherwise, I will start some other song here and end up at this point, maybe. Or maybe I start a song here and end up here, let's say. So that's what is the answer. Essentially, the sum of dp's divided by n is the answer at this time period. Otherwise, I start some song and I end up somewhere else with probability, right? With some probability, I end up listening to that song with my time and the song's time, right? Passed. So it's a pretty simple problem. I like the way this problem is structured. However, problem F is not a simple problem in the sense that I mean, it's a simple problem as well, but it's an implementationally hard problem. You have to consider all of these cases, and I talked about these cases, where first we have this Takahashi and cargo and this G here. This is the goal. And then you have to consider where Takahashi has to move first in order to push the cargo up to the goal. And then all of these here is the cases where Takahashi wants to move first, wants to position himself. And then for each of these, so for these solves where I want to solve them, sometimes there could be more possible ways to move. So sometimes it could be more optimal to move in some other location. That's why you check both of these locations, and I explain why in the live commentary. I won't repeat myself, but the idea is that for all of these positions here, Px and Py, where Takahashi will position himself, after that it's pretty straightforward into moving the cargo optimally to G. So moving the cargo optimally, it's just if cases here, just if cases, and we're updating the global answer with some answer. And I was surprised that this kind of passed from first try without any edge cases failed. So that's pretty much it. I will just refresh to see the editorial on G. There's no editorial here, but there's Japanese editorial here. So there's this max street theorem that we took a look, and I think in many cases the solution is sufficient. So the determinant can be found at most n, paying attention to the following. So one-time calculation determinant is this, what I said, n cubic, and this method takes, and all of these we can find this determinant. But then there's some there's some simplification to the n cubic solution. So well, I will take a look at this and see if I can understand it. But this is mostly heavy linear algebra. So yeah, thank you guys so much for watching, and I see you again in the next competition.